Hey everyone, Harsh here. We have been talking about scaling systems and handling load, but what if we could avoid doing a lot of expensive work in the first place? That's where caching comes in. Caching is a powerful technique to dramatically improve the performance and reduce the latency of your applications by storing frequently accessed data in a place where it can be retrieved much faster. Today we will explore different types of caches, where they live, and how they decide what to keep and what to throw out. So what's caching at its heart? It's all about storing copies of data that are frequently accessed in a temporary, super fast storage location is what we call cache. The idea is to keep data much closer to where it is needed. The main goal is to avoid delay and effort of fetching the data from its origin, often slower source every time. This original source could be a database, a remote API call, or even the result of a complex time-consuming calculation. The benefits are huge. You get much faster performance and lower latency because data is retrieved from speedy cache. It significantly reduces load on your backend systems, like your databases or other services. This means your overall system can often handle more requests or increase throughput, and it can even lead to cost savings by reducing expensive computations or data transfer fees. Think of it as your workshop. Instead of walking to your garage and getting the hammer, you already have it on your workbench. That workbench is your cache. Caching isn't just one thing. It can happen in many places. Broadly, we can categorize these locations into two main areas: client-side caching and server-side caching. Client-side caching is where the data is stored on the user's device within their local environment. You experience this all the time. Your web browser caches images, style sheets, and JavaScript files, so web pages load faster on subsequent visits. Mobile apps also cache data locally. Even your operating system does DNS caching. And on the other side, server-side caching happens on the application's infrastructure, on servers you control or use. This includes things like CDNs, caches within your application's code, database query caches, and caches at your API gateway. Both types are important for a comprehensive caching strategy. Let's look a bit closer at client-side caching. It is all about leveraging users' own device to store the data. The most common example being the browser cache. Your browser downloads static files like image, CSS, and JavaScript files and store them locally. When you visit the same page again or another page that uses the same assets, the browser can load them from its local cache instead of reloading them from the server. This makes pages load much faster and reduce load on your servers. This is typically controlled by HTTP headers like cache control. Mobile apps also do a similar thing, caching data for offline access or to make app fields secure. Even DNS lookups are cached by your operating system or browser that speed up connecting websites. The pros are it is incredibly fast, the user's data is right there, and it significantly reduces the network requests to your server. Cons are the managing cache consistency can be tricky. You need to tell the browser when to invalidate its cache. Storage is also limited, and you, as the server admin, have less direct control over it. Now let's shift to server-side caching. This is where the application developer or operator implementing cache within your own infrastructure to speed up things before requests even hit your core logic or primary data stores. There are several important types here, and we will focus on few key ones like content delivery network caching, application level caching, which can be in memory within your app or a separate distributed cache, and database caching. Other types exist too, like caches at your API gateway or specialized object caches, but these three are very common and impactful. First up, content delivery networks or CDNs. A CDN is a network of servers distributed geographically all around the world. Their primary job is to cache copies of your website's content, especially static assets like image, videos, JavaScript, and CSS files, on these edge servers that are physically closer to the end users. When a user, say in London, requests an image from a website hosted in California, instead of request traveling all the way from California and back, a CDN could serve that image from an edge server in or near London if it is already cached there. If not, CDN fetches it from your main origin server, caches it at the edge, and then serves it to the user. The benefits are enormous. You get a huge reduction in latency for users, especially those that are far from your origin server. It takes a massive load off your origin servers. It can even improve availability because if your origin server has a temporary hiccup, the CDN might still be able to serve cached content. Many CDNs also offer DDoS protection. Popular CDN providers include Cloudflare, AWS CloudFront, Akamai, and Fastly. Next, we have application level caching. This is where you, as a developer, implement caching logic directly within or closely alongside your application's code. This can be of two main forms. In-memory cache is where you store your application's cache data within its own RAM. It's extremely fast because there is no network call involved. However, this cache is local to the specific instance of your application. If you have multiple instances running, like an horizontally scaled setup, each will have its own separate in-memory cache, which can lead to inconsistencies unless the cache data is truly immutable. Simple hash maps can be used, or libraries like Guava cache in Java or Python's LRU cache. In a distributed environment, you use an external shared caching service. All your application instances connect to a central distributed cache. This ensures that all instances see the same cache data. Popular distributed caching systems are Redis and memcached. What do you cache here? Things like the result of complex calculations, frequently accessed data from your database, pre-rendered pieces of web page, and responses from other APIs your application calls. Databases themselves are often major performance bottlenecks, so caching at this layer is also very important. There are a couple of aspects to database caching. First, most modern databases have their own sophisticated internal caches. They will cache things like frequently accessed data blocks from disk into memory, precompiled query execution plans, and other internal structures. As an application developer, you often don't directly control this, but it's working behind the scenes to speed things up. Secondly, and more explicitly managed, is query result caching. This is where you cache the actual results of specific database queries that are run frequently. If you know a particular query is always fetching the same popular product details, you can cache its result instead of hitting the database every time. This can be implemented in your application layer, as we discussed in application level caching, or sometimes tools or proxies in front of database can do this. The main benefit is, of course, reducing the load on your database and speeding up data access. The biggest challenge with query result caching is caching invalidation. If the underlying data in the database changes, how do you ensure your cached query result is updated or removed so you don't serve stale data? This is a classic hard problem in computer science. Caches aren't infinitely large. They have a limited amount of space. So what happens when the cache is full and you need to store a new piece of data? You need to kick something out. This is called cache eviction, and the rules that decide which item are evicted are called cache eviction policies. Let us look at a few common ones. LRU, or least recently used. This is very popular. It discards the item that hasn't been accessed for the longest period. The logic is that if something hasn't been used in a while, it's less likely to be needed again soon. LFU, or least frequently used. This policy discards the item that has been accessed the fewest number of times. The idea here is items accessed frequently are more valuable to keep even if they weren't the most recent. FIFO, or first in first out. This is the simplest. It discards the oldest item that was added to the cache regardless of how often or recently it was used. It's like a queue. While simple, it's not often the most effective. There are other policies too, like most recently used, or MRU, or even random eviction. But LRU and LFU are very common in practice. The best policy often depends on specific access patterns of your data. Perhaps the most challenging aspect of caching is cache invalidation. This is all about ensuring that when the original data changes, the cached copy is updated or removed so that you don't end up serving old stale information to your users. Serving stale data can lead to all sorts of bugs and confusions. There's a famous quote in computer science that there are only two hard things in computer science: cache invalidation and naming things. And it's true, invalidation is tricky. But here are some few common strategies. One, we have write-through cache. When data is written, it's written to the cache and the underlying data store simultaneously, or the cache write happens first and then the data store. This keeps the cache consistent, but it means your write operations are now as slow as writing to both. Then we have a write back cache. Writes go directly to fast cache first, and then the cache then asynchronously writes the data back to the primary data store later. This makes write very fast from the application's perspective, but there is a risk of data loss if the cache fails before the data is persisted. Consistency with the main store is eventually achieved. Time to live, or TTL. This is a simpler approach where you set the expiration time for each cached item. After the TTL, the item is considered stale and removed or refetched. It's easy to implement, but you might serve stale data during the TTL window, or the data might even expire if it is perfectly valid. Active invalidation. This is where your application's code explicitly tells the cache to remove or update an item when the original data changes. This offers the most control and accuracy, but it can be complex to implement correctly across a distributed system. Choosing the right invalidation strategy is crucial, and it depends heavily on your application's tolerance for stale data versus performance needs. When you're thinking about implementing cache, here are a few key questions to ask. What data should you actually cache? Good candidates are data that are frequently accessed but doesn't change often, or data that's computationally expensive to generate. How fresh does the data absolutely need to be? Your tolerance for potentially stale data will heavily influence your choice for TTLs and invalidation strategies. Consider the size of the data you are cached and how it's accessed. This will help you determine appropriate cache size and eviction policies. You will want to monitor your cache hit versus miss ratio. A high hit ratio means your cache is effective, and a low one means it's not helping much. Always weigh the complexity of implementing and managing a cache against actual performance benefit you get. Sometimes a simpler solution is better. And be aware of potential issues like thundering herd problem. This is where a very popular cached item expires suddenly, tons of requests all try to regenerate at the same time, overwhelming your backend. You need strategies like cache stampede protection or staggered expirations to mitigate this. So the big takeaway is that caching is a fundamental technique for building fast, responsive, and scalable systems. By intelligently storing frequently accessed data closer to where it's needed, whether that's on the client side or at various points in your server's infrastructure like CDNs, application caches, or database caches, you can achieve dramatic performance gains. Remember to think about your eviction policies to manage cache space, and most importantly, have a solid strategy for invalidation so that your users see fresh data. A well thought out caching layer can be a game changer for your application's performance and user experience. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.